Before viewing the rest of this video, please read Chapter 4, the special case of two groups, the t-test. Given two samples or groups of measurements, you want to know if they were obtained from the same population. For example, two hypertensive drugs are given to two different patient groups. Is the arterial blood pressure different on average between the two groups? If so, what can you infer about the two hypertensive drugs? Assumptions for the t-tests are each sample must be randomly selected, the sample values are independent, all the sampled populations must be normally distributed, the variances of each population must be equal or comparable, even when the means are different. When comparing two groups or samples, we start with the hypothesis that they come from the same population. This is the null hypothesis. For example, the measurement of sample 1 can be averaged to provide a mean and a standard deviation. Similarly, with sample 2, there will be a mean and a standard deviation associated with those. Under the null hypothesis, the mean from sample 1 and the mean from sample 2 will be comparable, both of which should be comparable to the population mean. Similarly, the standard deviation measured in sample 1, standard deviation measured in sample 2 should be reflective of each other and the standard deviation of the population. From the limited sample data, how can we check if the sample means are estimating the same population mean? Well, one thing we could do is estimate the difference in the means and then the variability in the estimate of the difference in the means. From this, we create the t-ratio, in which in the numerator is the difference in the sample means, and the denominator is a standard error of difference of means. Thus, if the null hypothesis is true, we would expect that the mean of sample 1 is comparable to the mean of sample 2. Thus, the numerator, or their difference, would make t, our t-ratio, comparable to 0 or small. If the null hypothesis is false, then the mean from sample 1 and the mean from sample 2 will be different, and t, or the absolute value of t, will be greater than 0. So the difference in sample means is easy, but what about the standard error of the difference of the mean? How do we calculate that? So to calculate the standard error of the mean, we use the following property, where, for example, if x is a normal distribution defined by the mean and the standard deviation, and y is defined by the normal distribution defined by the mean and standard deviation, then the combination of x and y will be defined by a normal distribution defined by the combination of the means of x and y and the standard deviations, which is the square root of the sum of the variances of x and y. Therefore, the standard error in the difference of the means will be the square root of the sum of the variances of the two samples. Therefore, our t-ratio becomes the difference in the means of the two samples divided by the square root of the sum of the variances divided by the sample size. However, instead of using the individual variances of the two samples, we can use a pooled variance, which is just the mean of the two variances. So what is a small or large t? T-values corresponding to two random samples of size 10 drawn from the same distribution are shown below. In one case, the means are exactly equal. This gives us a t of 0. In another case, the means of the two samples are not equal, thus giving us a non-zero t. A histogram of t-values then can be computed from 200 observations, taking two random samples of size 10 from this population, and that's plotted here. Notice t can be both positive and negative, and for that case we always consider a two-sided t distribution. The shape of the t-distribution depends on the degrees of freedom, which is defined by the number of data points of the two samples minus the number of groups, which is always 2 in this case. So for the t-test, you compute the difference in the means and the standard error of the difference of the means. From this, we can compute the t-value. We need to determine the degrees of freedom to determine the shape of the t-distribution. For a given p-value, or alpha, in our case 0.05, we will determine if the t-value is greater than the critical value for the corresponding degree of freedom. If this is true, then we reject the null hypothesis, because the probability of sampling 2 groups from one population to achieve such a t-value was less than 5%. Next, I'd like to illustrate the t-test using R. For this example, please refer to box 4.1 in the text on page 59. We would like to compare total sperm motility between 2 groups who have low amounts of cell phone use and high amounts of cell phone use. In the low cell phone use group, we're going to randomly sample a normal distribution of 120 points with a mean of 60 and a standard deviation of 19. In the high use, we're going to sample normal distribution 62 times with a mean of 57, standard deviation of 17. We can then see for the samples that we have drawn for both groups by using a box plot. And we can see that they are relatively symmetrically distributed with medians that are very close to each other. We can perform a t-test on these 2 groups using the t-test function. And assuming that the variances are equal. The output of the test gives us a t-value of 0.062. The degrees of freedom were calculated by the sum of the 2 sample sizes to give us a total of 182 minus the number of groups to give us a degrees of freedom of 180. The p-value tells us that there's a relatively high probability of picking 2 groups from the same population to give us a t-value of 0.062. We can illustrate this by plotting the t-distribution for 180 degrees of freedom from This is the t-distribution for 180 degrees of freedom. We are interested in the two-sided distribution, where both positive and negative t-values are possible. We have a tolerance of error, or an alpha value, of 5%, which means that we would consider t-values at the top 2.5% and the bottom 2.5% to be within this threshold. We can retrieve these threshold t-values using the quantile function of 0.025, 180 degrees of freedom, gives us a value of minus 1.97, which is very close in this region here. Similarly, we can calculate the opposing value. We can plot these on the graph. Thus, for any t-value within these two boundaries, we would consider the null hypothesis true. Any t-values outside these thresholds in the wings of the t-distribution, we would consider the null hypothesis false. The total area under the curve between these two thresholds is 95%, and the remaining 5% is evenly distributed between the two wings. If given two samples with the mean and standard deviation of each, as well as the sample sizes, and the sample sizes are different, this needs to be taken into account in the calculation of t. Again, when performing this calculation with the given mean and standard deviations, you should always use a pooled variance estimate. The degrees of freedom remain the total number of points minus the number of groups, which is 2. Sometimes you would like to compare if the mean value for a specific population is significantly different from a reference value, given a sample data from that population. In this case then, the numerator becomes a difference between the sample mean and then the reference value, and then the denominator, the standard error in the mean. The degrees of freedom is the total number of points minus the number of groups, which is 1. If we wanted to perform this test in R, we would take our sample data and the t-test function, and we would compare this to the true value of the mean, mu, which we set equal to that reference number we want to compare. If no mu is entered, then the default value of mu is 0, so the sample data then is compared to a reference value of 0. Some common errors in the use of the t-test. The t-test should be used only to test the hypothesis that two sample means are not different. When the hypothesis involves more than two samples or groups, you must use analysis of variance, or ANOVA. When t-tests are used to test differences among multiple groups, the true p-value will be the reported p-value multiplied by the number of possible t-tests. Thus, we need to account for multiple comparisons. So to review, with ANOVA, we can test the hypothesis that two or more groups are from the same population. If we reject the null hypothesis using ANOVA for 3 or more groups, we can then further define how many populations are being represented by using pairwise comparisons using the t-test. As an example, given 3 samples, we would like to know how many populations are represented. Our first step would be to perform an ANOVA. If our F value is sufficiently high, then we reject the null hypothesis and know that at least 2 populations are represented. Then we can perform pairwise comparisons among the 3 groups to determine how many populations are present. However, the p-value in multiple comparisons changes. In the single case, when the probability of erroneously rejecting the null hypothesis is related to alpha. If we now test k hypotheses using the same data, the probability of erroneously rejecting is now raised to the power of the number of tests. Thus, if we are going to perform 3 tests with a tolerance for error of 5%, then our p-value, or our actual alpha, becomes 14%. Thus, we need a correction for the effective p-value in multiple comparisons. Another way of thinking about this is if I take a 2-sided coin and I ask you, what are the odds that I get a head? You would tell me that the answer is 50%. However, if I now flip the coin twice, my odds of getting at least 1 head goes up to 75%. And this is the effect of having multiple tries or multiple comparisons on our effective tolerance for error, or p-value. Thus, in our general scheme, we want to first apply ANOVA, we proceed to multiple comparisons only if ANOVA rejects the null hypothesis. If there are m samples or groups, the total number of comparisons can be figured out if we want to compare all the groups to each other by this relationship here. So for 3 samples, the number of comparisons that we make will be 3. One way to compensate for multiple comparisons is Bonferroni. In this case then, our threshold alpha value of 0.05 is reduced by a factor of the number of comparisons that we plan to make. So if our alpha value is typically 0.05, but we want to make 3 comparisons, then for each of the pairwise t-tests, it will be compared to 0.05 divided by 3. If for the different groups we are given the mean and standard deviations, we can use the variance within and its corresponding degrees of freedom to calculate the t-values. Another way of compensating for multiple comparisons is through the home compensation or home t-test. In this case then, we compute the t-values as in Bonferroni, except this time we arrange the comparisons in descending order of the computed t-value. The threshold t-value used to compare with each comparison is calculated by the number of remaining comparisons. Thus, if we were to make 3 comparisons, then the largest t-value is compared to the threshold value with alpha divided by 3. The second highest t-value is compared to the threshold t-value of alpha divided by 2. And then the last comparison is made to the t-value of alpha equal to 0.05. At any point within the comparisons that the t-value does not exceed the threshold value, then the comparisons are halted, and the null hypothesis is considered true for the remaining comparisons. Home-Sidek is similar to home in that we also compute the t-values ahead of time and then arrange the comparisons, as in home, from largest t-value to smallest t-value. However, this time the alpha value for each comparison is calculated using this formula based on the number of comparisons, the total number of comparisons k, the iteration, and then the alpha of the threshold. If I have 3 total comparisons, for my first comparison, this fraction is 1 over 3 minus 1 plus 1, so it's 1 over 3. For my second comparison, this exponent is 1 over 3 minus 2, and then for my third comparison, it's 1 over 3 minus 3 plus 1 in the exponent. At any point during these comparisons that the t does not exceed the t threshold, the comparisons stop and the null hypothesis is considered true for the remaining comparisons. So what test should we use? Well, a liberal test rejects the null hypothesis too often. A new treatment that is as effective as a standard one can be erroneously considered better than the standard. This is when the null hypothesis is falsely rejected. A conservative test accepts the null hypothesis too often. A new treatment that is in effect better than the standard one can be erroneously considered equal than the standard. This is when the null hypothesis is falsely accepted. Home or Home-Sidek are usually tested first. Both give practically the same results, although Home-Sidek is the one usually implemented in stat software packages. At the end, however, the selection of the test depends on the particular hypothesis.